Okay, I hope that I'm well audible. It is a great pleasure for me today to present the work of one of our one of our doctoral students, Jikai, who is working on a topic that is one perhaps not, let's say, not directly associating with artificial intelligence, but more on that in a few moments. So, artificial intelligence has not only changed the way people are working at TRUMPF, but has already found its way into various products. So here's a very, due to the lack of time, a very brief overview. So in sheet metal production, for example, where we have access to large amounts of data on the shapes of individual cut objects, we use machine learning for material saving, part design through to, let's say, efficient sorting and packaging. In my company's laser technology division, for example, we use sensor data to optimize laser material processing and to control the relevant laser parameters. So this could be, for example, optical coherence tomography signals for remote welding of aluminum housing for e-mobility applications. So the institution where these techniques are used is the famous TRUMPF Laser Application Center in Ditzing, Germany. So the main idea of this facility, where I'm also engaged at, is that our customers do have access to our products, so to our optics, to our lasers, also to the system technology, and especially also to the experience of our application engineers, and that they can come to us and test whether a particular laser application, so this is mainly based on material processing, works or not. And in this institution, we also have access to the latest light sources, and one of these lasers is on the screen. It's a 2 micro 9000 series lasers that delivers ultra short pulses at 1 kilowatt average power and 10 millijoule pulse energy. So in fact, next to our PhD student, one can see the heart of this amplifier, which is a disk-based multipass cell. And I don't want to bore you with laser parameters, but a laser like this, which is already a product, can generate 10 to the power of 16 watts per square centimeter. So this laser is generating such high intensities that any material where the radiation interacts with would vaporize immediately. So we are therefore dealing with, let's say, very destructive pulses that can only be cleverly used if optical concepts are employed, where the radiation is, let's say, distributed onto large areas or into the volume of the workpiece. And this is done simply by beam shaping. And this means that we are adapting the spatial shape of the laser focus and optimize it to the respective application. And the prime example for this is for beam shaping concept is on display. It's about transferring a Gaussian shape into a flat top with very homogeneous intensity profile. And this works well if the beam quality is at the diffraction limit, which can be seen here on the top row, so the ideal case. However, a real-world laser, as it is as the one that has been discussed before, so typically shows deviation from this ideal profile in amplitude and in phase. And although the beam quality of a laser like this, a 2 micro 9000, is already extraordinarily good, so in terms of m square, it's even better than 1.2. The corresponding shape flat top, which can be seen on the bottom right, shows already a uniformity error of about 50%. So this is exactly where we come in with machine learning, because we want to use poor intensity signals, as can be recorded simply with cameras, and to figure out what the laser radiation is missing. For example, we want to predict wavefront aberrations that might reduce the beam quality, as it is the case here on the bottom with, for example, a certain very well-defined phase or a certain very well-defined amplitude distribution. So for this task, we set up a standard adaptive optics setup that consists of the spatial light modulator. So it could be a deformable mirror or a liquid crystalline silicon-based spatial light modulator. And the laser beam characterization part now is not a typical interferometer or Jacques-Hartmann sensor, but is a very simple and low-cost intensity-only setup that is recording the near and the far field of the laser beam under test. With this information, we will later control back the deformable mirror to ensure best beam quality for certain applications. So for our deep learning concept, we are using a large set of near and far field measurements. So we only have 2 intensity signals, and those intensity signals are mapped with the corresponding phase aberration that is trained and that is displayed, for example, with the spatial light modulator during our training phase. So here we are using a zonal-based convolutional network and use image-to-image transition from the measured input intensity, which is a stack of gray values, and that is, as mentioned, mapped to a certain phase distribution, which is at hand at the raw beam of our illuminating system. So if you want more details about this convolutional network, I can refer to the reference that is shown here. I would like to provide a simple example of our phase prediction. So on the left-hand side, we can see a, let's say, very interesting intensity profile. So it's asymmetric, doesn't look like that the beam profile is at the diffraction limit. And this is also confirmed by a defocused image, which is recorded by camera 2. So as we know from the spatial light modulator, what is the ground truth of the wavefront, we can compare it to the predicted result. And we have been very interested in here because the absolute difference of that phase or wavefront difference was better than lambda over 10. And this was achieved by, let's say, training data with 20,000 signals. So with the spatial light modulator, it took us about 1 hour to do that. So as the prediction already works, we now want to see if also the compensation is good. And on the, let's say, on the one of the correlation results is displayed here. So the first column shows the intensity signal for the reference, so an ideal beam quality in the near field and also in the far field. And in the second column, let's say arbitrary aberration is shown again in these intensity signals of near and far field. And now we apply the correction, and I would like to emphasize that we didn't do anything with, let's say that the only metrology at hand was these 2 intensity signals. And the correction is, let's say, very close to our reference beam with an M² parameter that is very high. I would like to summarize this point. So we have presented a machine learning-based low-cost device that is enabling in situ laser beam wavefront correction, and the phase prediction accuracy is let's say better than lambda over 17. And with an approach like this, we would like to demonstrate that at TRUMPF we do know our, let's say, laser sources very well. We can characterize them in detail, and based on these very detailed characterization, we can design completely new laser application strategy to the corresponding beam shaping and optimize the laser material processing strategy. So with that, and with this very close look into source modeling and laser beam characterization at TRUMPF, I would like to thank you very much for your attention, and I'm happy to answer some questions. Thank you.